Some of the biggest questions we can ask are also the simplest. And for a long time, the answers felt like they were locked away, hidden behind impossible math. But then came Stephen Hawking, and he had this incredible gift for making the entire universe feel, well, understandable. So today, we're going to use his masterpiece, A Brief History of Time, as our map to explore those huge questions about where we all came from. I mean, these are the big ones, right? The kind of stuff you wonder about when you're looking up at the night sky. For centuries, they've fascinated everyone. But modern science got so complicated that, honestly, most of us feel like we can't even begin to ask. Hawking's whole point was, no, we absolutely can. And in fact, we have to. And really, who better to be our guide on this journey? I love this quote because it captures him perfectly. He wasn't just bogged down in the equations, he could see past all that to the fundamental dance of geometry behind everything. It's like he saw the cosmos not just as a machine, but as this beautiful, elegant structure. He was basically a master translator for the universe. Okay, so to really get where Hawking is coming from, we first have to rewind a bit. We've got to see how our most basic ideas about how reality works got completely flipped on their head. This is the story of how we went from a simple, predictable universe to one that is a whole lot stranger and, honestly, way more interesting. For the longest time, the universe, in our minds, belonged to Isaac Newton. And his view was pretty common sense, right? An hour for you is an hour for me. A foot here is the same as a foot on the other side of the planet. Time and space were just this fixed, unchanging stage where everything happened. Seemed obvious. But then, a little crack started to show in that perfect picture. Hawking uses this brilliant, simple example. Imagine you're on a train, and you're bouncing a ping pong ball. To you, the ball is just going straight up and down, maybe a foot or so. But what about someone standing on the platform, watching your train whiz by? From their point of view, that ball isn't just going up and down, it's moving forward with the train. It's traveling a much longer diagonal path. So who's right? The answer is, you both are. And that simple idea shows there's no such thing as an absolute distance. It all depends on who's looking. And that little thought experiment leads us straight to Albert Einstein, who basically took that crack and blew the whole thing wide open. It was a total revolution. Gone were the ideas of absolute space and time. Suddenly, they were flexible, they were relative. And the biggest shock of all, gravity. Gravity wasn't a force anymore. It was something else entirely. So if gravity isn't this mysterious force pulling us down, then what on earth is it? This, right here, is one of the biggest aha moments in the history of science. Einstein gave gravity a brand new secret identity. It's not a pull, it's a curve. And here it is, general relativity. The big idea is that something massive, like the sun, doesn't pull on the Earth with some invisible rope. Instead, the sun's immense mass actually bends and warps the very fabric of space and time around it. Think of it like putting a heavy bowling ball on a trampoline. It creates this big dip, this curve in the material. That curve, that's what we experience as gravity.
So check this out. This is the key. The Earth isn't being forced into orbit around the sun. It's just moving in a straight line. But it's a straight line through curved space-time. And that path is called a geodesic. It's the exact same reason an airplane flying from New York to London flies in an arc over the globe. It looks like a curve on a flat map, but it's actually the shortest, straightest path on a curved surface.
And this is how we know it's true. I mean, this is the beautiful proof. If gravity is just curved space, then everything has to follow that curve, even light. And sure enough, it does. During a solar eclipse, astronomers saw it happen. The light from a star way behind the sun was actually bent as it passed by, making the star look like it was in a different place. It was this incredible confirmation. Einstein was right. Okay, so if a little bit of gravity can bend space and time, what happens when you take that idea and you turn it up to the absolute extreme? Well, that question takes us right to one of the most bizarre and famous objects in the entire cosmos, the black hole. I mean, it is the ultimate trap. Think about that trampoline again. But instead of a bowling ball, imagine you drop something so incredibly dense that it doesn't just make a dip, it rips a hole clean through the fabric. That's kind of what a black hole is. It's a spot where gravity has become so intense, the curvature of space-time becomes a bottomless pit. And Hawking gives us this amazing play-by-play of what it would be like to watch one form. So a giant star dies and starts to collapse in on itself. An astronaut on that star is sending out a little signal every second. Now, a spaceship watching from far away sees those signals start to arrive further and further apart because gravity is literally stretching out time. Finally, the star collapses past a certain point, and the signal the astronaut sent at 11 o'clock just never arrives. To the spaceship, time on the star has ground to a complete halt. The star's light shifts to red, it gets dimmer, and then, poof, it's gone. A black hole is born. And what's at the very center of that black hole? Well, something we call a singularity. It's this theoretical point where all the stuff from that huge star is crushed down to a spot with basically zero size and infinite density. It's a place where all our rules, all our known laws of physics, even Einstein's, just stop working. They break down completely. It's the ultimate cosmic question mark. The fact that things like singularities exist at the heart of black holes and maybe even at the very beginning of the universe in the Big Bang, that tells us something really important. It tells us our picture of the universe is not complete. And that brings us to what is basically the holy grail for all of modern physics, the hunt for one single theory that can explain, well, everything. So the big challenge is to bring our two greatest theories together. On one hand, you've got general relativity, which works perfectly for describing huge things like stars and galaxies. On the other hand, you have quantum mechanics, which is amazing at describing the super weird world of tiny particles. The problem? They don't play nice together. They give different answers for the same questions. A unified theory would be the one single framework, one beautiful set of laws that works for everything, big and small. And, Hawking himself said it best. Finding this theory isn't just about coming up with better math. It's about something much, much bigger. It's really the final chapter in a story that started thousands of years ago, when the first humans looked up at the stars and just wondered. It would be, as he so powerfully put it, the ultimate triumph of human reason. And this is the final amazing thought that Hawking leaves us with. Just imagine, what if that final theory, that one perfect equation, was actually simple enough for all of us to grasp, at least in its basic ideas? If that happened, could we all, not just scientists but everybody, finally join the conversation about the deepest questions of all? Why are we here, and why is there a universe in the first place? It's just a totally mind-blowing thought to end on.